Hello, everyone. Welcome back. This is Chapter 7 of General Chemistry, Thermochemistry, and Thermodynamics. Thank you guys so much for tuning in again. Thank you for being patient with me. Hello to the Zoom chat. It's been a minute since I've seen you guys. I took a little break for Ramadan and also to study for my shelf exam, internal medicine, and I have my board exam in 8 weeks. So please pray for me. I would love to hear from some of you guys about how the MCAT prep is going. Once again, as always, if you'd like to support the channel, we have 3 ways of supporting down in the description below. I have a Buy Me a Coffee page, I have a Patreon, and I have my Venmo listed below. 50% of everything that we make from this channel goes towards charity through Doctors Without Borders, and I send you guys the receipts through email and WhatsApp. Speaking of WhatsApp, join the WhatsApp group, sign up for the email list, which I have to be better at emailing. And thank you guys so much for everything that you do for me and for yourselves. I am so incredibly proud of all of you for making it this far. And if you're studying for the MCAT and you're struggling, just know that you have a community with us and you're always welcome. So thank you so much. Okay. So let's begin talking about thermochemistry, right? So the first part of thermochemistry is talking about these 2 things called systems and processes. Systems and processes, right? So a system is basically the matter that's being observed, right? So if I'm saying that I'm doing a experiment within a flask, all the stuff inside of the flask and the flask itself is the system that I'm observing. And that sort of, environment of the flask is contained within the system. So the inside of the flask, the walls of the flask, everything that's stuck to the walls of the flask, all of that can take part in the experiment, and that's why it's part of the system. But the process is a little different. And also, when we're talking about systems, we need something that's not the system, right? And we call the thing that's not the system, so we're going to say negative system, right? And that's going to be the environment. So that's the environment or the surrounding, everything that's not the system, right? Okay. Now we have 3 different types of systems that we need to know about. So number 1, let's zoom in a little bit so it's easier for you guys to look at. Number 1 is an isolated system. And instead of going through each of the systems one by one, I'm just going to write them all out once and then we're going to go over them. So 1 is an isolated system, 2 is a closed system, and 3 is an open system. An isolated system cannot exchange heat or work or matter with the environment. So, and heat and work is contained within what? It's contained within energy, right? So it doesn't exchange energy or matter with the environment. What's an example of this system? This would be an insulated bomb calorimeter. The styrofoam cup with like the top on it and the temperature probe and everything. A calorimeter, just a insulated calorimeter and nothing else.
Right, sure.
An insulated calorimeter. All right. So a closed system will exchange energy, not matter. A closed system exchanges energy, not matter. Can you guys stop flirting in my chat? That's what the WhatsApp chat is for, not the Zoom chat. Okay, a closed system is something like a steam radiator. Right? And then an open system, if this one doesn't do either, this one does one, then this one does both. So it exchanges energy and matter with the environment. What was the environment again? It was everything that's not inside the system, right? An example of this is a boiling pot of water? Makes sense, right, guys? Yes? So that was about systems, right? What about processes? Well, a process is a change in one or more of a system's properties. So if you have a pot of water and you put it on a fire, right, and the energy is exchanging into it, the temperature is going to go up. And that's a process. That's a process that's happening to the system, right? And we track these changes in the system and these processes that are happening through a couple of laws of thermodynamics. So let's talk about the first law of thermodynamics. So the first law of thermo states that delta U equals Q minus W, right? So this is the change in internal energy of a system equals the, oh, I can't even read my damn handwriting. Look at that. Hold on. Oh, I've told you guys the funny story that I was going to tell you before. This is Q is the heat added minus work done by the system. So let's think about this, right? Let's think about this. If you have a system and you heat it up, right? One of two things can happen to that energy that you just put into the system. One, the energy can go towards doing work. It can go towards an output. For example, when you burn gasoline inside of a car engine, it turns the pistons, which in turn give energy to the axle, which turns the wheels and moves the car. That's work that's done. And that's from the heat that was added, right? But not all of the heat added goes directly towards work because nothing is 100% efficient. So there's some heat added that just comes out as heat. That's why a car engine gets hot. If a car engine was 100% efficient, it would take all of that heat and turn it into work. We can't create 100% efficient machines. Make sense? What's the third word for you? Change in internal energy of a system. Cool? Cool, yes or no? If you say no, I'm kicking you out. Kidding. Okay. There are 3 types of processes. Well, now I know your last name, so maybe don't say not cool in my chat before I dox you. This is not a safe space. No, it was never a safe space. Any space where I'm lecturing is not a safe space for a student learning because I will come for you if you got anything wrong or if you disagree with me. This is not a democracy. I was going to make a really nasty joke about he's on a lot of lists, but...
We know. We know the joke.
No, I'm kidding. Guys, I'm a very nice person, I promise. It's some people's first time here. Let's not scare them away. AMC back dictator. Yeah, that's mad funny. Okay. There are 3 different types of processes, right, that you need to know about. And obviously processes, like we were saying, are changes that happen inside of the system, correct? Like we said, let's scroll back up. Change in one or more of a system's properties, right? So the properties of a system can change in 3 ways, right? So there can be an isothermal process. Right? There can be an isothermal process. I don't know why I'm writing so slanted today. Oh, I think it's because my board is slanted. Whatever. There can be an adiabatic process. Am I the only one who how do you guys write on your notebooks? Like some people I see, they write with their notebook straight up. I have to bend my notebook at like a 45-degree angle to write on it.
Yo, no joke. My friend writes with her notebook upside down.
You're joking.
I'm being so serious. It's literally upside down. It's the only way she can write.
No, but like, how does that work?
But the handwriting ends up right side up?
Yeah, and her handwriting is flawless. Like,
Does she write from like the bottom up?
No, she writes normally, but like her hand is bent in a way. Okay, so I wouldn't say like 180 degrees. I'd say like 145, you know?
It's very strange.
Her handwriting is amazing though.
Interesting. I would need to see that. Okay, so anyways, isothermal processes, adiabatic processes, and isobaric processes, right? So in isothermal processes, the temperature is held constant, right? And because the temperature is held constant, let's take a look at something, right? Let's take a look at something. If the temperature is held constant, what sort of is like the ramification of that on the first law of thermodynamics, right? If the temperature is held constant, we're kind of assuming that the internal energy over here is constant throughout the process. And that means that we can rewrite this expression to say that in an adiabatic process, the heat added is equal to the work done by the system. And this is exactly what I was saying earlier about the car engine, that if the car engine was 100% efficient and there was no change in the temperature of the system, then we would have a perfect conversion of the heat added to the work done. So an isothermal process is a perfect reaction, right? It's a perfect reaction. And sometimes, you know, the AMC, like if you look in the Kaplan books, everything like that, they're going to give you these charts, like what an isothermal process looks like under a chart with like the pressure versus the volume. I don't think that's super important. Maybe I don't think it's important because I never understood it. Maybe I don't think it's important because out of 9,000 MCAT questions, I never saw it come up. Who knows, right? Can I go over it one more time? Okay. This is a pot of water. Inside this pot of water, or I guess outside this pot of water, there is a stand. And this stand has a little fan on it. The steam from this water is going to rise and boil and turn the fan, right? I am going to add heat in the form of a fire. The heat that enters this boiling pot is going to create steam that's going to turn this turbine, and then it's going to connect into a wire that's going to output energy this way. If this were absolutely 100% an isothermal process, the temperature of this water would never go up. It would stay at 100 degrees Celsius exactly as the steam was produced and turns the fan. That's it. That's all that would happen, right? But that's not what happens. The temperature of this and the vessel is going to go up because some of the heat added is going to go into the vessel. Some of it's going to escape out into the environment. Some of it's going to go into the water molecules. Some of it's going to hit the gas around here. Some of it might even hit the fan and warm up this whole apparatus, right? It might warm up stuff over here, everything. So if the temperature of this whole thing were constant, that means that the heat added is equal to the work done, which is the spinning of the fan. Does that make sense? Okay. That is an isothermal process. Yippee. Okay. Adiabatic processes are basically when Q equals 0, right? The heat added equals 0. So the change in the energy is equal to negative W. Right? There's no heat exchange. Why is it negative? Because heat has to be lost by the system in order to do work. You can't increase the heat and you can't increase the internal energy and increase the work. The energy needs to be turned into work. So if you're doing work, you're losing energy in the system. Does that make sense? I feel like I understand this better now than I did last year. Laura can vouch for me. Okay? You were there when I taught this last year. Okay. Isobaric processes, the pressure is constant. I'm still sweating from the dog's thread. Don't sweat. Don't sweat. If I somehow find out your address, I'll just send you a gift before your MCAT. Don't worry about it. Okay. This actually does not alter the law. It doesn't change it in any way because the pressure is not included here, right? So it's still delta U equals Q minus W. My birthday's coming up soon. When's your birthday? Happy birthday. $420. Look at that. Wow. All right. One more. Isovolumetric process. Guys, what's the formula for work in physics? Work equals force times distance times the cosine of the angle upon which the work is done. Let's forget cosine theta for a moment. Let's just say on a flat plane, that's force times distance, correct? So if we are inside of a chamber, what is the distance? How do we track the change in the distance? We'd have to use it using volume. If we have an isovolumetric process, that means there's no change in the distance that something is moving or the amount of space that's moved, which means there's no work done, which means that no work done because no change in volume, which means delta U equals Q. However much heat you put in, that's how much the energy changes inside the system. Under isobaric process, it says it does not alter the law of thermodynamics, the one that we were talking about up here. It looks exactly like this for an isobaric process. So you can see each of these actually has its own little sort of tweak of the first law of thermodynamics and the way that we approach it. Here is the 1,000-year-old question. And virtual Jolly Rancher for someone who gets this absolutely correct. Also, I am considering swapping back to whiteboard, so you guys should be excited.
You write even worse on whiteboards.
I don't think that's true.
Your videos from last year were literally always illegible.
Oh, well. You'll deal. Seems
I won't deal. I'm not walking.
seems that it's good enough for 12,000 people and you're the only one complaining. Anyways, a spontaneous process. Guys, what is a spontaneous process? What is, wait, someone said it. Someone said it. Hold on. Go back. Wait, everyone stop typing. Okay. Samia was the one who said it first. It doesn't require energy. So spontaneous process, remember what a process is. It's a change in the properties of a system, correct? And if we're changing the properties of a system, if there's some internal change that's happening, we're saying that this change is occurring without input of outside energy. Right? So it's a process that occurs without outside energy input. Make sense? Who's the one who transcribes my meetings all the time? It's okay. Like I don't mind it at all. I just want to know who it is because it always happens every single time that we're here. Okay. Right? And like someone said before, the delta G of a spontaneous process would be negative. The Gibbs free energy, which is sort of an elusive concept to a lot of people who are studying general chemistry, right? And we know that the delta G equals the delta H, which is the enthalpy of the reaction, the change in the enthalpy of the reaction between the reactions and the products, minus T delta S, the temperature multiplied by the change of the entropy, right? So ideally, in order for delta G to be negative, we want delta H to be negative and delta S to be positive, right? Since we're here, let's do this little chart, which is actually very important for the MCAT. So let's do the delta G, the delta H, and the delta S, right? I also love this chart. I really, really, really love this chart. It's very helpful because it shows me how well all of the students know algebra. Ice charts are better. Of course, the person who wants to deport everyone thinks that ice charts are better. Freaking racist.
Yo, quit talking like that before I ask you for your registration and your license.
Okay, so if delta H is negative and delta S is positive, we already said that the delta G is going to be negative, right? Because this is going to be positive right here makes this whole term negative, and negative here, negative plus a negative is negative delta G, right? So obviously, if we swap these, this is going to be always positive, and this is always negative. Okay, now let's talk about the other. If we have a negative delta H and a negative delta S, let's take a look at this. So if this is negative, that's favorable. That's what we want. But if the delta S is negative, we multiply it by a negative T, this becomes positive. So obviously we don't want the positive to influence the negative, which is favorable, too much, right? Okay, so if the negative is to be not overwhelmed by the positive over here, we need this to be as small as possible. So this is going to be negative or spontaneous at low temperature. Spontaneous at low temperature. Make sense? Okay. Then we have positive and positive. Obviously, the positive is wanted here because the negative delta T times the positive makes that negative, which is what we want. We want delta G to be negative. But then the positive delta H, right, is not what we want. So we need this term right here to be large enough to cancel out the positive delta H. So this is going to be spontaneous or negative at high temperature. What even is the meme with those rose emojis? Oh, okay. By the way, the story I was going to tell you guys. So let's take a little break here. So obviously I was moving my entire setup back to my home, back where my parents live, and and I pack everything up. I bring the suitcase and I pack every single thing up, and it's a lot. It's 2 monitors, my keyboard, my little trackpad, my microphone, all my wires, my light,
You get it. You have a bunch of stuff.
everything. And no, it's just so much stuff, and like all the adapters and the like microphones for TikTok and whatever it is. And I bring all of it. I bring every single thing. And now I'm setting it all up, and I'm like opening up everything and putting it out, blah, blah, whatever it is. And I put out my keyboard, and then I realized I'm just like, oh my God, I don't have my mouse. So my mouse is sitting back in my apartment, lonely, just hasn't been brought. And now I'm scrambling. I was just like, oh my God, it's literally been like a month since I've lectured, and I don't want to cancel this lecture because I told everyone that we were going to be, around. And now the thing is, it wouldn't be a problem because I have a touchscreen monitor, right? My main monitor is an all-in-one desktop, and it's touchscreen. However, my second monitor is not touchscreen, right? So I need a mouse to be able to move stuff between the two of them. So right now I have 1, 2, 3, 4, 5 things open, right? And one of them is just my GoodNotes, which is taking up the entire main monitor. So I need the outer monitor for the 4 other things. And there'd be no way for me to put them over there. And I was just like, I mean, like, I would be able to kind of balance everything on one screen, but it would just be absolute chaos. It would be absolute freaking chaos. So thankfully, I found my Magic Mouse, like my Apple Magic Mouse, that was like buried in my bag since I haven't used my laptop in some time, and I was able to pair it with my computer. So that's what I've been using, and that's why I haven't been able to scroll as efficiently as normal. But that was the funny story of today. Just use your brain to move the cursor. I'm not smart enough for that. I'm not smart enough for a lot of things.
More panicky than funny.
This is funny to me.
It was funny that you lost your mouse and you didn't bring it with you.
No, I mean, it's not lost. It's just sitting there.
I would be inherently panicking.
What's there to panic about?
You forgot the mouse that moves everything on the screen. That's like level 1. That's like code blue. Like, you forgot your whole mouse.
So what?
What are you supposed to do? What are you supposed to do? Grip the screen with your fingers and like what if you eat something and then you have to touch your screen with your fingers and everything is getting gross and sticky and you need your mouse. That's like super important.
See, guys, this is the difference between someone who has been to medical school and is used to being stressed and someone who has not lived life.
No, I just needed to make the story more interesting. That was kind of boring, not gonna lie.
That's okay. I can't please them all, you know what I mean? You're getting pressed by little kids. Possible. Okay, so there are 2 things that spontaneous...
I'm not little. I'm about who said that?
Can you shut the hell up? All right. There are 2 things that spontaneous isn't. There are things that spontaneous is, and there's things that spontaneous isn't, right? Spontaneous is not what? What's the first thing that spontaneous isn't? It's not fast. Yeah, it's not fast. It ain't Ramadan anymore. It's not fast. Right? And there's one more thing that spontaneous isn't. Spontaneous does not mean that the reaction goes to completion. So spontaneous doesn't need to be a fast reaction, and spontaneous does not mean that the reaction needs to go to completion, right? So there is one example of a spontaneous reaction that happens very, very slowly. And I give this example every time I give this lecture and whenever I talk about thermodynamics. What is that reaction? Anyone? Diamond deterioration? Well, no. I don't even know what that entails. What is a reaction that you see regularly in life that is spontaneous but very, very slow? It's actually the rusting of iron. The rusting of iron is a very slow, spontaneous reaction. Burning, I don't know when's the last time you saw something burning slow that wasn't a candle. Okay. My MCAT progress. Okay. Now, this is an important pearl of knowledge, right? Where's it burning? Where you at? I'm going to show you something. Okay. This is a very important pearl of knowledge, right? In biochemistry, in the body, right, we couple non-spontaneous reactions to spontaneous reactions. What do I mean by that? What do I mean by that? Here is GTP. GTP breaks its phosphate bond and turns into what? Let me share some of my old wisdom. Turns into GDP and PI. Can someone tell me 2 of the reasons why this releases so much energy? The cleaving of that gamma phosphate bond? It's 2 reasons that this releases energy. Number 1, it releases energy through negative charge repulsion. Exactly. Very good. The negative O's are unfavorable, so breaking the bond is good. Very good. So negative charge repulsion. The phosphate breaks off and it gets repelled from the rest of the molecule. So there's less negative charges clustered together. Yeah, no, this very smart student. Last one is resonance stabilization. Very good. So the two terminals, the phosphate that just got kicked off, was already resonating at the end of the GTP molecule, but now it's resonating by itself away from everything else. But the new terminal that you created on the GDP is now resonating as well. So you have more resonance, right? So that's why that happens. Now, you couple this favorable process to a unfavorable process, which is taking amino acids and turning them into peptides. Right? Does that make sense? Guys, the funny people are smart. Funny people are very smart. All right. I'm not saying anything. Not saying anything. Okay, now obviously the reformation, I guess reformation. The reformation, I actually took the MCAT and got a 132 in Chem Phys, but I'm gonna retake. What? Huh? Wait. Huh? You're 19? Wait, hold on. Whoa, no. You're 19. You took the MCAT already. You got a 132 in Chem Phys, and you're retaking. Someone explain. Someone explain.
Tanya, you either have to turn your microphone on or turn
Okay. Let me.
Thank you.
I'm listening.
Okay.
I'm gonna stop everything. Explain.
Okay. Basically, I don't know what happened, but I didn't do so hot in cars and psych, even though I was doing great, like on AAMC full lengths. And so I got a 515. I'm sure you can do the math.
What? You got a what?
No, stop.
You're retaking a 515.
You're retaking a 515?
Where are you right now? I'm not.
Wait. Let me finish. I'm in a BSMD program.
Never scored.
Guess what score they require? Guess.
516.
Yep.
No way. That's
No.
okay.
Pause.
Did you talk to them? Did you
Pause.
talk to them though?
Everyone stop.
No, they're really strict.
Everyone stop. What BSMD program are you in that requires a 516?
I go to USF.
Oh my. Apply out, dude. At this point, apply out. Like, I'm being so serious. I'm being so serious.
Because 516 is crazy.
That's insane.
Our program is a 503, I think.
Oh,
Like they don't even.
Dude, mine was like, I know I got a 521. My requirement was a 509.
That's what I'm saying. Your program is ridiculous. That's ridiculous.
Yeah,
You should listen. You need to talk to them. You need to talk to them.
Okay, guys, listen. Let's continue this conversation after we finish teaching. We will take an intermission after we're done, but we have to speak about this a little bit. Let me finish, and we will figure out something to do together. Anyways, the reformation of GTP from GDP and can you teach this, dude? Like, I don't want to do this.
Seriously, just be quiet. Let her do it.
Okay, so the reformation of a GTP from GDP and an inorganic phosphate group is obviously not a favorable reaction, because we just said that the favorable reaction is the cleavage of that gamma phosphate bond, right? So in order to reform that bond, we need to couple that to a reaction that's actually favorable, right? Okay. So let's take glucose and let's turn it into CO2 and water and heat through glycolysis and the TCA cycle and oxphos. And I'll give a cookie to anyone other than Samya other than Samia who knows which step the GTP comes from? Specifically. Succinyl-CoA. Exactly. When you turn succinyl-CoA into succinate, you get GTP. Why is that? Well, you're turning a thioester into a carboxylate. So you're taking a very electrophilic thing and you're turning into a very stable thing, which are both carboxylic acid derivatives. And that is going to make your GTP, which is taking a anhydride, turning into phosphor anhydride, right? Okay. Does that make sense? Does it make sense how this is unfavorable, this is favorable, and it cycles this unfavorable, favorable reaction down this little spiral, right? We get to recycle this over and over and over again. Does that make sense? I'm very happy that there's someone inside of the chat who can like call me on my BS if I get something wrong.
Dude, I think we have 2 of those people. But he's refusing to score drop right now. I'm gonna crash out. You guys are crazy. And they get out of here. Is it your exam in like 2 days?
Okay, wait. To be completely honest, what's it called? Retaking like this is the last thing I'll say about this until the lecture is over. But retaking a 515 might not be as crazy as I'm making it seem, because a 515 was like just barely competitive when I was applying, and I was applying 3.5 years ago, obviously, right? So like it really depends on where you are, and plus Florida, super competitive, really competitive state for medical school.
I feel like it's more nuanced than that, because she's literally right at the score cutoff.
No, she is. It's hard.
I feel like she could get away with talking to them and being like, hey, do you really want me to retake for 1 point?
It's hard. I mean, that happened to a lot of Brooklyn College, that people were like 1 point away and they appealed. But like our school is very open to appeals. That's the thing.
Our school isn't, and someone still appealed and they got away with it.
Right. So. You're in Texas at what? No, wait. Texas is like one of the most competitive schools for medical. What are you talking about? We're going to talk about states and state functions. Only thing about Texas is that they really only take their own. So that might be driving the score down. Yeah, if you're a resident, exactly. That's the key term. If you are a resident. Yeah, no. Average in New York City right now is roughly a 517. And that's if you're a resident or not. All right, anyways, state functions. State functions are macroscopic properties that describe the system at equilibrium. These include and are not limited to pressure, volume, Gibbs free energy, density, enthalpy, entropy, temperature, internal energy. And in order, this is P, V, G, rho, H, S, T, U. Chances of doing chapter 8 today? Is chapter 8 gases? I might hold off. I might do chapter 9, but I might hold off on chapter 8. Just have to review it. When did Fatima get here?
Make Samia teach gases.
Yeah, Samia, do you actually want to teach a lecture for me? Okay, you can. You're more than free. No, not right now. No. If you actually want to teach, I'll let you prepare for it, and you can do it next time. Guys, should we do lab techniques after this?
Someone was crashing out about that earlier.
I'm pretty awake, so I feel like we can get through it. We might do lab techniques. Yeah, let's do it. Why not? All right, let's do it tonight. Okay. State functions. So those are your state functions, right? And then we have process functions. And these are descriptions of the pathway from one equilibrium state to the next equilibrium state. So basically, a system is going from one state to another, and we want to describe the way that it got there. That would be a process function, right? Then we talk about standard conditions. Then we talk about phase changes. Let's do the phase change diagram for sure. We'll do that. Okay, it's a long chapter. I forgot how long this chapter is. Okay. Let me take a look at this, see what else we need to talk about. Standard conditions. Let's just do a quick note about that. STP is 273 Kelvin and 1 atmosphere. That's standard temperature and pressure. Standard conditions is a little different. Standard conditions in thermodynamics is 25 degrees Celsius, which is how much Kelvin? Anyone? 25 degrees Celsius is how much Kelvin? 298. Very good. How'd you get that? How'd you get it? 273 plus Celsius. Very good. You guys are on point today. Very sharp. Okay. We also have 1 atmosphere of pressure, and we have 1 molar concentrations of anything that we have inside of any flask. Very good. Okay. Now, question. And at standard conditions, right? This is something that a lot of people don't make the connection of. Standard conditions is basically what we're saying when we say, what is bromine at standard conditions? What is iodine at standard conditions? What is calcium at standard conditions? Well, this thing is a liquid. This thing is a solid, right? What's that thing you said about 22.4 liters? What's the importance of 22.4 liters? This is going to be 1 mole of gas, correct? It's 1 mole of gas. Very good. Never forget. Yeah, of course. Never forget 22.4. You can answer so many questions with that. There's actually a question on a completely unnamed, unbranded, unknown Q bank the other day. And it says, let's say you have 1.5 grams of nitrogen gas and you have 1.5 grams of oxygen gas. What is the difference between the volumes occupied? So nitrogen occupies more. Oxygen occupies more. Both occupy the same. Or can't tell. You need more info. So Lath says get moles and then compare using 22.4. Right. So let's take a look at that. Let's do B, C, N, O, F. Nitrogen is lighter than oxygen. So what has more moles? 1.5 grams of nitrogen or 1.5 grams of oxygen? Nitrogen has more moles, correct? And if it has more moles, then it's going to take up more or less space? It's going to take up more space because we already know that 1 mole is 22.4 liters. So you have more moles, it's going to take up more of that potential 22.4 liters. Does that make sense? So nitrogen is going to take up more space because it's lighter. And within that 1.5 grams, there's more of it. Basically, the way that we described gas density. This is actually important to thermodynamics. I'm glad that we touched upon this in this lecture. Very good. Can I get a blue Jolly Rancher? Yo, someone get this guy a Jolly Rancher, man. All right, let's look at real quick. Let me open this up. Let me get you guys a phase change diagram. All right. Cool. Let's do this one. Let's drop it right here. All right. Very low quality, but that's all we need. Who up changing the phase right now? All of us. Here's solid, here's liquid, here's gas. The triple point where all three of them exist at the same time, right? And we're going to label these. We're going to label these, right? Okay. Solid to liquid is what? Is melting. Liquid to solid is freezing. Very good. Liquid to gas is evaporation. Gas to liquid is condensation. Solid to gas is sublimation. And gas to solid is deposition. Very good, because the gas deposits as a solid. Very good. Those terms you need to know like the back of your goddamn hand. Rapid fire. You need to know those off the top of your head like there's no tomorrow. Okay, so that's all we'll do about phase changes. But there is one more thing I want to talk about with phase changes, and it's the way that the curve is oriented. Okay, so let's take a look at the heating curve real quick. We'll do it like this, and then like that, and then like this. Oops, sorry. Do like this, and then like this, and then like that, and then like this, and like that. Question. I hate that. Question. What's happening at these points where the temperature is constant, but the energy is increasing? I'm talking about the energy of the actual stuff, right? What's happening? Someone mentioned that phase changes are happening here. You're absolutely correct that at this point, it's a solid. At this point, it's a liquid. And at this point, it's a gas. And as we continue to put energy into the system, the gas and the solid and the liquid heat up. They heat up to a specific point, and then over here we have the solid to liquid transition, and we have the liquid to gas transition. And what's happening is that over here, at this point of the curve, our energy is being used to heat up the temperature of the specific sample of the solid to make the molecules vibrate faster in the solid. That's what's happening. But then when we get to the solid to liquid transition, we've reached a temperature which for water is 0 degrees Celsius. We've reached a temperature at which the energy is now being not put into vibrating the molecules of the solid, but to break the intermolecular forces between two water molecules. So let's say we have a water molecule here and a water molecule here and a water molecule here and a water molecule here. Now at this point, the solid to liquid transition, the energy is being put to split the hydrogen bonds between these. Does that make sense? Then once again, when we have the liquid where all of these intermolecular interactions between the water molecules are broken, we have the liquid heating up again. The temperature is being increased. The water molecules are shaking up again. They're getting faster and faster. We're about to boil the water, and now the water is just about to boil, and it shoots off. Because now there's enough energy that's been put into this to break the intermolecular interactions between the liquid water molecules. Does that make sense? And you will see this as the heat of fusion and the heat of vaporization. Does that make sense? Yes? Thermo is hot. Thermo is a little hot. Not gonna lie. I'm jealous. Maybe that's why I don't like this chapter.
You could never boil like Thermo does.
I can't. I'm too cold. I'm too nonchalant. One more thing. What the hell does this mean, guys? This guy just called me Ankyo. Someone kick him out of the chat. Yes, I know what it says. What does it mean? What the fuck? You think I can't read? What does it mean? Okay. The amount of energy needed to raise the temperature of a mass of something given the specific heat capacity of that object, right? So this is an amount of energy. This is the mass of your sample. This is how much energy 1 gram of that sample absorbs to increase by 1 degree of whatever temperature you're using, multiply by the temperature. Question. If you sat here and I gave you a second, could you figure out the units for specific heat capacity? Could you do it? Yes, you could. Yes, you could. Q, energy, is measured in what? Joules. Mass is measured in grams. T is measured in Kelvin or Celsius. So if all of this needs to cancel out, right? Let's just set everything equal to C. So Q over MT equals C, correct? So that means that joules per gram degree Kelvin equals C, or degree Celsius. C is given normally, yes, but I'm asking you if you could figure, that's not the point. I'm asking you if you could figure out the units of C. So it is the amount of energy needed to increase 1 gram of a substance by 1 degree Kelvin. Someone please double check me on this. Go look up the units for specific heat capacity.
You're right.
Thanks. I've looked at this since sophomore year of high school. It's been about 5 years now, but could still be wrong. No, not 5 years. It's been
a decade.
9 years now. Yeah, it's been about 9 years now.
Yo, I was actually making that as a joke. I didn't think it was actually a decade.
Yeah, it's been 9 years. I was 16. Now I'm turning 25. Yeah. I started high school in 2014. I was 15 as a sophomore, turning 16. Unk. Yeah, I know. Oh, well. Oh, wow. I literally had it on the next page of my notes. Ha! Funny. Okay, we can go over the calorimeter, but I don't think it comes up often enough for me to want to... Bro was in high school and Dan Daniel... Yeah, I was. I remember that. I think I was in my sophomore year. We went over the heating curve already. enthalpy? Okay, let's do this. Do you guys see how much more lively the lectures are now that I'm out of medical school? Can I skim the calorimeter types just for you? No, because I'd be pretty bad at teaching them. I suggest that you find someone else to teach them to you. Enthalpy. It's a state function, right? It's a state function. It can be calculated and analyzed as a system undergoes change. When's my research year? In a couple months. Starts in July. Yeah, after step 2. So as the system undergoes a change, we can calculate the enthalpy, right? And the change in enthalpy is delta H. MD, PhD? No. No, absolutely not. There are only 3 ways out of medical school. You graduate, you drop out, or you die. Well, I'm not dropping out, and I haven't graduated yet, and hopefully I don't die. So technically, I'm still in medical school. My enrollment is still valid, but just taking a little break. All right. But I guess that's a good point. Okay. So delta H is the heat transferred into or out of a system at constant pressure, right? The delta H of the reaction equals the enthalpy of the products minus the enthalpy of the reactants. Bro has a sparkle in his eyes again. It's funny. It's like life is worth living again, you know? I came home. After my exam, I came home. I read a book. I lit some bahur, made my room smell good. Got to pray without thinking about anything else. Read my Quran, had a little drink, made some tea, had a little bit of baklava. It was it was good. It was good. Huh?
I said, can you stop flexing?
Life was good for one day. And I have to start studying for step 2 on Monday. So I'm going to enjoy. Alhamdulillah. Alhamdulillah. I was very relaxed. Yeah. For the first time in a while, I can say that I was relaxing. It was good. It was good. And it's stuff like that you really enjoy after working for that long. And I hope that all of you guys get to experience that after your MCAT as well. Nice. Okay, so we know about the delta H. And now we're going to talk about changes in delta H. So if the delta H is positive, we call that an endothermic process. I'm so scared. And if the delta H is negative, we call that an exothermic process. Which of these is more favorable? EXO, why? Not because we're fans of The Weeknd, but why is EXO more favorable? If you got that reference, shout out to you. Yo, question? Yeah, what's your question? What's your question?
Well, now I'm shy. Now I can't see.
Exactly. So exothermic is more favored. Why? Well, let's go back to our diagram that we had a couple pages back. Right here, right? And you saw that when the delta H was negative, that was the favorable component, right? That when the delta H was negative, we didn't want to ruin it with a high temperature. We wanted to have it with a low temperature. And also the delta H being negative led to this always being spontaneous. So We want a negative delta H. We want an exothermic process. So if you were to plot the enthalpy of the reactants versus the products, it would kind of look like that. That the products have a lower enthalpy than the reactants, which would give you a negative delta H. Does that make sense? Yasmin, I'm not gonna ask for you, and you wanted all these people to hear your questions, so
No, I don't want them. We're chilling. It's fine.
suit yourself.
Listen, this is a private exothermic matter, okay?
Exo means heat is going into the system. No, it means it's escaping actually. Because look, the enthalpy, which is the heat transferred into or out of the system, is lower in the products than the reactants. So things are escaping. What's the actual reason it's favorable? Because it leads to a favorable delta G. That's why. It sets up for a spontaneous reaction. That's why it's favorable. The system is the reaction. No, the reaction happens in the system. Guys, let's go back. Hold on. Let's go back to basics. Let's go back to the top for 1 second. Okay? The system is the matter that's being observed. The reaction that's happening is happening to the matter. So any change in the system is going to be observed as a change within that matter. So if something's exothermic, that's a process that's happening to the matter. The matter is releasing enthalpy, releasing energy. Exo is favorable and endo is not favorable. Exactly. That's what I'm saying. Okay. Make sense? Yes? No? Maybe? Very quickly about enthalpy, Hess's law. Anyone ever play with Hess trucks as a kid? Is this being recorded? Yeah, it's going to be posted on YouTube. Hess's law. Enthalpy changes are additive. My troubles are going to be posted on YouTube. If you want me to cut them out, I can. Let's say you go from A to B, and B to C, and C to D. LOL, it's fine. Oh, thank God I don't have to do extra work. Okay, so we have delta H1, delta H2, delta H3. No, I'm being very serious. If you actually want me to cut them out, I will. And it's not going to be too much of a hassle for me. I just have to make a single cut in the video. All right. Let's call this delta HX, right? Question is, what is delta HX equal to? Well, since we went from A to B and B to C and C to D, the transition from A to D would actually be additive of all of them. So delta HX would be delta H of the first reaction plus delta H of the second reaction plus delta H of the third reaction. Now, any one of these could be positive or negative. Any one of these could be endothermic, exothermic, doesn't matter. What we're saying is these are the intermediate steps. Intermediate step 1, intermediate step 2, intermediate step 3. And if you add up the intermediate steps, if you add up the delta H of the intermediate steps, the change in enthalpy of the intermediate steps, then you get the change in enthalpy of the overall reaction. Does that make sense? Yes? Good. We talked about Gibbs free energy. Okay, we can talk a little bit about entropy. There's really not much to say. Honestly, the only thing about entropy I want you to know is that the entropy of the universe is always increasing, right? And the fact that it's like the randomness, the disorderliness of whatever's going on. Make sense? We already went over Gibbs free energy. We talked about delta G equals delta H minus T delta S. There's one more thing we have to talk about. And we'll call it a day with this chapter. There are some other stuff that I didn't touch upon that I just want you guys to know, and it's that you might be asked to calculate the delta H of the reaction using the delta H of bond enthalpies versus heat of formation, right? Stuff like that. Just go over those sort of equations, right? It's not too bad. The different delta G formulas is what we're doing right now. Yeah. Okay. Delta G equals delta H minus T delta S. We know this, right? We know this. However, there's some other stuff that we need to know. Who here knows what KEQ is? Or a better question, does anyone want me to explain what it is? Does anyone want me? There's no real analogy. You have to build up to it. So let's explain it again. Let's say that you have a process. Forget the letters. Forget this. Okay. You have acetic acid. And acetic acid dissociates into a hydronium ion and an acetate ion. And you want to ask yourself how much of this is actually happening, right? How much of this is actually happening? You can say that there is a K, an equilibrium constant, that tells you how much of this exactly is happening. And it's actually the concentration of the products over the concentration of the reactants. And the reason that this is so important is because it's telling you a ratio of how much product there is versus how much reactant there is. So it's telling you what's more favorable. If this thing is greater than 1, then we know that the products are more favorable than the reactants. And if it's less than 1, then we know that the reactants are more favorable than the products, because the denominator being greater means that we're going to have a lesser number. The numerator being greater means we're going to have a greater number. However, what does that mean about the stability? If the right side is more stable, we're obviously going to push more towards it, which is going to drive up this number, right? And if the left side is more stable, we're going to push more towards it, which is going to drive down this number. So basically what the K is able to tell you is which side of this reaction everything's going to get pulled towards, correct? But is that not sort of the same as spontaneity? Does that not tell you something about the forward reaction, right? Because if the forward reaction is less stable, there's less of a desire to do it, right? There's less of a desire to perform the forward reaction if it's not made up of favorable components. Let's say that someone wanted you to become 40 pounds lighter than you currently are. That's hard, and it's probably not favorable. Losing 40 pounds would be pretty unhealthy for a lot of people, right? So if someone wanted you to do that, you'd be resistant to do so, right? But if someone told you, oh, well, just lose 5, maybe, like, I could lose 5 pounds. Let's take me, for example. I can't lose 40 pounds. I'd probably be very sick, but I could lose 5, right? So I could be there, right? It's a stable place for me to be. So if it's stable over here, the forward reaction actually happens. And the forward reaction happening is contingent upon what? How spontaneous the reaction actually is. So the way that we sort of equate these two things is that we take the K of any equilibrium sort of, reaction, right? We take the K, we say delta G also equals negative R, which is the gas constant, times the temperature, and the natural log of K. And we thereby equate delta G to K. And you can see the more positive and greater that K is, And it has to be greater than 1. Why? Because we're taking a natural log. Natural log of anything less than 1 is going to be negative, right? And it's going to cancel out this negative and make that positive, right? So what we're saying is that the greater the K is, the more negative the delta G. It's much easier to see this way. If we say negative delta G equals RT ln K, and then ln K equals negative delta G over RT, and K equals E to the power of negative delta G over RT. I said it was easier to see this way. Maybe not, but this is also a little conversion that you can do. Does that make sense? You guys have been hearing me yap for so long. It's 11:56. Oh my God. I've been yapping, man. I've been chatting.
Good question. Before you close this chapter, I was wondering if you could like explain the other one with the E, the delta G with the E, like the reduction potential.
This one?
As well.
This one?
Yeah, like a little bit more on that one.
You'll have to wait until the electrochem chapter, because I would have to build this up from zero. I can't really explain it right now. I do have a video out on it right now, but like you can watch it from last year, but it's not something I'm capable of doing at the moment because I need to explain what reduction potentials are. But for someone who already knows what reduction potentials are specifically, as we said, the greater the reduction potential of a specific metal, right, the more it wants to be reduced, right? So there are a specific species, not just a metal, but the more something wants to be reduced, right? So let's say that you're looking at oxygen, right? And you have oxygen reacting with some metal X with a very, very, very low reduction potential. The cell that's produced between them is going to be E equals E reduced minus E oxidized, which is going to be more negative. So, more positive, because the oxygen has a very positive reduction potential. So that is going to drive this very high up, and then you just multiply by the number of electrons in the equation and Faraday's constant. And both of these really don't matter all too much, because you're sort of just taking them on a case-by-case basis, and Faraday's constant is a constant, of course. So really, you're just equating the delta G to the reduction potential of the cell, which makes sense when you think of the idea that the reduction potential is contingent upon how much the metal wants to be reduced. Does that make sense?
Yes. Also, I just joined, so I'm not sure. Did you make that table, the one with all the
I did.
delta H
Yes,
stuff?
I did.
I'll just go back.
I did. Yeah, you can watch the lecture on YouTube.
Great, thank you.
No problem. So high equilibrium constant, product favorability, negative delta G. Exactly. That's exactly a perfect summation of what I said. So the equilibrium constant is product over reactants, and this being high means the products are favored. And if the products are favored, that means we have stability on the other side, which would make this a spontaneous reaction. People, does that make sense? Okay. I need to do a little bit of studying before I teach the gas phase, or Samia can do it for me. And that'll be it. That'll be it for this chapter. That was a long lecture. It was a long lecture to be the first one that I did on my way back. But thank you guys so much for watching. Once again, if you'd like to support the channel, please check out the description below. Every single one of you is so special to me, and thank you so much for sticking around and helping me out with a dream of mine. Thank you guys, and I'll see you soon. Zoom chat, stick around.